In match problem 2, we're considering this provided Cobb-Douglas production function. X represents units of labor, Y is units of capital, and we're given some costs for each of those units. In part A, if $300,000 has been budgeted for production, how should the amount be allocated in order to maximize production, and what's that maximum production? So essentially what we're trying to find is, out of this budget, how much should we spend on labor, how much should we spend on capital? So we know that we have a total of $300,000 to spend, and that $300 is going to be spent by spending $40 for each unit of labor, so 40 times X, and $120 for each unit of capital, so plus 120Y. So this ends up becoming our constraint function. Even though it wasn't provided for us explicitly, we've got the information here that we need in order to build it. So step 1, we want to state our problem. What we're trying to do is maximize this Cobb-Douglas function, n of xy equals 20x to the 0.5, y to the 0.5. And this is subject to the constraint. Again, we need to take this equation, set it equal to 0. So subject to the constraint, 40x plus 120y minus 300,000 is equal to 0. So in step 2, we need to construct that function capital F, which is f of x, y, lambda. So in this case, that's going to be 20x to the 0.5, y to the 0.5, plus lambda times each of these terms, so plus 40x lambda, plus 120 times y times lambda, minus 300,000 lambda. In step 3, again, we'll take the derivative of this function with respect to x, then with respect to y, then with respect to lambda. So our derivative with respect to x will be 10x to the negative 0.5, y to the 0.5, plus 40 lambda, and we'll set that equal to 0. We'll find f sub y, which is going to be 10x to the 0.5, y to the negative 0.5, plus 120 lambda, and set that equal to 0. And then we'll find f sub lambda, the derivative with respect to lambda, which will be 40x plus 120y minus 300,000. And set that equal to 0 as well. So what we'll do first is look at f sub x and f sub y, derivative with respect to x, derivative with respect to y, and solve each of these for lambda. So if we solve this for lambda, we would subtract this expression from both sides and then divide by 40, which will give us negative 1/4 x to the negative 0.5, y to the 0.5. Similarly with our derivative with respect to y, this will give us negative 1/12 x to the 0.5, y to the negative 0.5. So now what we're going to do is take each of these expressions that we've come up with that are solved for lambda. Since they're both equal to lambda, whatever it is, it means they both have to be equal to each other. So we'll take negative 1/4 x to the negative 0.5, y to the 0.5, and set that equal to negative 1/12 x to the 0.5, y to the negative 0.5. Now what might be helpful at this point would be to rewrite these as rational expressions, rewrite these with positive exponents. So we could rewrite this as negative x to the 0.5 over 12y to the 0.5. And we could rewrite this as negative y to the 0.5 over 4x to the 0.5. So a step you may or may not need to take, but essentially what we're going to end up doing is cross-multiplying here to get 12y equals 4x, and then solving for y, we'll get y equals 1/3 x. So we know that y equals 1/3 x, which means we can come back to any of these three equations, plug in that value for y, solve for the corresponding x value. So we could take f sub y, which is going to be 40 times x plus 120 times 1/3 y. I'm sorry, we're not looking at f sub y, we're looking at f sub lambda. So that's going to be 40 times x plus 120 times y, which we're going to substitute in 1/3 x, minus 300,000. All of that is set equal to 0. So solving for x in this case should give us x equals 3,750. So we know what x is, we still don't know what y is, so we can look at f sub lambda again. This is going to be 40 times 3,750 plus 120y minus 300,000 set equal to 0, and then solving for y is going to give us y equals 1,250. So now we can come back to either of these two expressions. We know what x and y are. So if we plug in our values for x and y into either of these, we should be able to solve for lambda. So for instance, lambda could be found by taking negative 1/4 times 3,750 to the negative 1/2 times 1,250 to the 1/2, or 0.5. I'm not sure why I switched to 1/2 instead of 0.5 there, but for some reason I started making that switch. So evaluating this is just a calculator operation, substituting that into your calculator, which is going to give us lambda is approximately equal to negative 0.1443. So solving that system was a little more rigorous in this case, but we still only came up with one critical value. And our only critical value is x equals 3,750, y equals 1,250, and lambda equals negative 0.1443. So that tells us that our function n of x comma y is maximized at 3,750 comma 1,250, and that our max profit or I'm sorry, not our maximum profit, our maximum production is at n of 3,750, 1,250, which is approximately 43,301 units. So what we're saying is if we spend $3,750 on capital, $1,250 on, $3,750 on labor, $1,250 on capital. I apologize, I messed that up twice now. Let me say this one more time. We're spending $40 on labor. That was given to us in the problem. So if we spend money on 3,750 units of labor, each of those costs $40, and we spend money on 1,250 units of capital, each of those costing $120, then our production is going to be maximized at a little over 43,000 units. So now in part B, we want to find the marginal productivity of money and estimate the increase in production if an additional $40,000 is budgeted for production. So we can find the marginal productivity of money as the opposite of our value for lambda, which in this case is the opposite of negative 0.1443, or just 0.1443. So we take that value, multiply it by the change in the increase in production. Sorry. Take this value, multiply it by the increase in our budget. So we're going to increase our budget by $40,000. So we take that increase times our value for lambda, gives us a result of 5,772. So if we increase our budget by $40,000, then we increase production by 5,772 units, approximately.